Let's take the data that we have and analyze it using an Excel spreadsheet, which is a really useful tool. I've set up the basics of the spreadsheet except for the calculation sections. I've got the data table, the masses of the three measurements that we have, and then I've set up a table where I've got the amounts and molar mass, but all the calculations are blank. As you can see, I've got the masses bold-faced in red, and if you go to the class website underneath labs, you'll find out that you can download this spreadsheet. I rounded the masses out to 1/100th of a gram because, as you saw, the balance thousandth was fluctuating back and forth a bit. So to be honest in terms of reporting the data, even though the balance showed those numbers, I don't think they were that valid. So to be honest in saying what the masses were, I'm going to round these off to 1/100th of a gram. Well, let's start doing some calculations. Now, the mass of the baking soda, NaHCO3, sodium hydrogen carbonate, is going to be the subtraction of the mass that we had of everything, that baking soda in the pan, which I'll highlight, and then make this calculation by typing an equal sign to indicate that I'm doing a calculation. You can see it's up here. I'm going to take the mass that I have here of the baking soda, highlight that, and which is that cell B6, and subtract from that the mass of the empty pan and cork and let it do the subtraction for me. And in fact, as soon as you put your own data in, this will change depending on what you put in. The mass of the sodium carbonates can be done easily too, which is that mass of the sodium hydrogen carbonate with the pan and the cork minus the pan and the cork, which was the same value here, and voila, we've got that subtraction taken care of, and any data that you put in here will give you these two critical pieces: the baking soda you start off with and this sodium carbonate that you're going to get at the end. Now here I've got the equation set up where two sodium hydrogen carbonates produce one sodium carbonate, and water that escaped as steam and carbon dioxide that escaped as steam. And I want to know the moles of these to figure out what's going on, but I've got to start with the mass in grams, so I'll just put down equals, what I calculated over here. I'm not going to redo the subtraction, and there it is, the 28.21 grams. Now for the first real calculation, when you change this gram amount into the chemist's amount, the actual amount in terms of these particles, all you have to do is, for this calculation, make our little equal sign again, and realize that we're going to have to take the mass and divide it by the grams per mole molar mass. That's something you should be doing automatically now. That's something you shouldn't even think about. And that will give you the moles of the baking soda, the real amount. That's pretty typical for a molar amount. Usually they're less than 1. Now I had 4 significant digits here, and my actual molar mass of the sodium hydrogen carbonate is 84.007, but the 4 sig digs is all you need. And my answer should be the 4 sig digs. Now, if you wanted more than that, which wouldn't really be accurate, you could change the view of this decimal. But I really think, 4 is about the best we could do, judging from those fluctuations because of the hot pan. Now, the sodium carbonate is going to depend on the molar amount of the sodium hydrogen carbonate. We see 2 of these makes 1 of these. So this is going to be easy. All I have to do to calculate this, I'll put my equal sign in and take whatever this mole amount is and divide it by 2. And I get my answer to 4 sig dig, which is about right. Actually, the moles of steam and the moles of the carbon dioxide will be identical to that. And if you wanted to find the grams of water that escape and the grams of CO2 you put into the atmosphere in this experiment, that could be done very easily in this spreadsheet. Here, I've done the calculation already. Here's the molar mass of the sodium carbonate. 2 sodiums plus 1 carbon plus 3 oxygens, 105.99. And this calculation, you see, I've done it already. I've taken my I5, which was the moles, and multiplied it by the molar mass. If I take moles and multiply it by grams per moles in dimensional analysis, that's my mass of baking soda that I should have produced theoretically. If this thing was heated perfectly and I didn't have to worry about convection currents and so forth, I would expect to get 17.79 grams of sodium carbonate. Now, here's what I actually got, 17.71. That's pretty close. And for this experiment, considering that we had moisture in the air and those convection currents, I'm pretty pleased with this. And I can find the percent error pretty easily. Percent error is going to be equal to my experimental data, what I ended up getting. You put your data first. You always put yourself first on percent error. But I better use parentheses because there's a subtraction. So I'm going to take this mass that I ended up getting, which was the 17.71, and subtract that from what I should have gotten. Yours minus the expected. And that will end up getting us the deviation. You know, how many grams did I deviate from the right answer from? You can see I was off by roughly 1/10 of a gram, which isn't much. I mean, a gram isn't all that much. So, but I want the percent error. My value was a little bit lower than what it should have been. I should have gotten 17.79, but got 17.71. And the lift due to the hot pan could have accounted for that. But I didn't want deviation. I wanted percent error. So I'm going to have to take this and divide by my expected value. And my expected value divided by was my I7. I'll put that in directly and enter. And the percent error is I make this my percentage. So there we go. 0% error. Let me expand that. Oh, 0.5% error. That rounded off to 0. Typically with percent error, showing it to the nearest whole percent because there's a subtraction involved in this. And when you get that subtraction, at the best, you're going to get one significant figure usually. But this is it. There's my percent error. In fact, I'll leave it at the 0.5%, which is, well, I'm happy with that. Again, just using a balance and an oven. And you can do a prediction for a chemical reaction. Very, very nice.